I'm Brian. I'm going to talk about our new paper on fast kurtosis imaging. Diffusion kurtosis imaging, or DKI, is a way to quantify a non-Gaussian diffusion in each image pixel. This deviation from Gaussian diffusion is caused by the tissue microstructure, and therefore DKI is typically referred to as a microstructural imaging technique. If you average the observed kurtosis over all directions, you get what is called the mean kurtosis, and this is a biomarker that has shown potential in connection with many diseases. Clinical application, however, is held back by the rather large data requirement for DKI and also the rather long post-processing times that are connected with DKI analysis. So a fast method for mean kurtosis estimation would be helpful for clinical application, clinical exploration, and even in basic research. Our technique for fast kurtosis imaging is very similar to the idea behind rapid estimation of mean diffusivity, where measurements along 3 orthogonal directions is enough to provide an estimate of mean diffusivity as simply a sum of log signals. This is because the mean diffusivity is tied to the trace of the diffusion tensor, and you may probe these tensor entries with 3 orthogonal directions. Similarly, if you define a mean kurtosis related to the trace of the kurtosis tensor, as shown here, you can probe the tensor entries needed to form the tensor trace and get the mean kurtosis in that way. However, the kurtosis tensor is of higher rank than the diffusion tensor, and so more directions are needed to estimate the mean kurtosis. And in fact, 9 directions are needed to do this trick. The central expression is then this shown here on top of this slide, where a weighted sum of log signals acquired along directions ni, ni plus, and ni minus, and the index I goes from 1 to 3, so there are 9 directions in total. And this sum of these log signals adds up to a number which is the sum of this minus BD term here, and then a kurtosis term which is proportional to B squared. So we can see here from the equation that if we know the mean diffusivity and have measured the signal along these 9 directions, then we can estimate the mean kurtosis using this expression. This was the basis for the 139 scheme for fast kurtosis estimation that we showed in our MRM paper from 2013. The 139 scheme collects one image at B equals to 0 for normalization, and then 3 orthogonal directions at B1, and the 9 directions at a B value B2. The 199 scheme that we present in the current paper also acquires one image at B0, but then the 9 directions are acquired at both B1 and B2. And this allows us to form the equation on top of this slide for both B values, B1 and B2, so that essentially produces 2 equations with 2 unknowns, the mean diffusivity D bar and the mean kurtosis W bar. And then we can isolate for these 2 parameters, and we get closed form expressions for both mean diffusivity and mean kurtosis in a framework that's exact to order B squared. Estimation fidelity will depend critically on the choice of the B values B1 and B2. Here we show results from a numerical B value optimization and an experimental B value optimization. This is A and B respectively. The error landscape shows the combined error on the estimate of mean diffusivity and mean kurtosis, and we see that the overall structure of the two landscapes is the same, and that a low error region is present in both cases for B1 equals to 1 and B2 around 2.5 inappropriate units. We also map the performance of the techniques, the 139 protocol in red and the 199 protocol in green, and for this benchmarking we use a non-linear least squares fitting algorithm applied to a large dataset consisting of 150 images as a basis for comparison. The SNR level is shown on the x-axis. We have white matter in panels A and B, and grey matter in panels C and D. A and C show the performance for mean diffusivity, and B and D show the performance for mean kurtosis. The shaded areas in these plots represent the standard deviation, and the markers show the mean values over noise realizations. And we see that for realistic SNR levels of maybe 30 or 40, the 199 protocol performs almost comparable to the nonlinear least squares fitting to a large data set that has more than 7 times as much information as the 199 protocol. And we also see that the 199 protocol consistently outperforms the 139 protocol. So all in all, these simulations show the 199 protocol to be quite efficient. The estimation fidelity is also very dependent on the acquisition being carried out with the prescribed directions and p-values that are constant among the directions. This is not always the case, so we wanted to evaluate how much such deviations affect the 199 protocol. So we perform simulations for grey matter and white matter, where we allow the directions to be imprecise, and we also allow the b-values to vary among the directions, and then we present a method to repair such imperfect acquisitions. If the encoding directions deviate from those prescribed by theory, or if the b-values vary among the directions, the data cannot be analyzed as shown here. Instead, the weights in front of the log signals would have to be redistributed so that the measurement tensors for the rank 2 and the rank 4 case become as close as possible to the identity tensors. Then the basic relation is re-established as shown on the bottom here, but with weights that are determined from a linear fit, and the b bar is then the shell average b-value. Here we show the result of simulations to map the effect of imperfect encoding on the 139 estimate of mean kurtosis and the 199 estimate of mean kurtosis. These simulations are for grey matter. The x-axis shows b-value deviation from 0 to 10% among the directions, and the y-axis shows the amount of angular deviation that we allow each direction to have in these simulations. When we compare the performance in A and B, we see that the 199 protocol, the method, is much more robust to these imperfect encodings than the 139 method. On the bottom row in C and D, we show the effect of the correction scheme when applied to the same data as shown in A and B. This shows that the 139 error landscape can be flattened somewhat, so that the large error seen for a high b-value deviation is removed somewhat, but large errors remain, whereas in the 199 case in D, we see that the correction scheme is able to almost completely remove the high error region, so that even quite bad datasets can be used for 199 estimation. The picture is the same in white matter, where again we see the 199 protocol to inherently be much more robust to imperfect encodings compared to the 139 protocol. This is A and B, and in C and D we show the effect of applying this correction scheme to the 139 case in C and the 199 case in D. As in gray matter, we see that correcting 139 datasets is possible but not very efficient, whereas the correction scheme is very efficient for correction of 199 data, even for cases where the deviation from perfect encoding is quite severe. So in summary, we have presented an extension of the original fast kurtosis technique that we published a few years ago. Using 19 standard diffusion-weighted images, we provide estimates of mean diffusivity, mean kurtosis, and FA with precision and bias comparable to state-of-the-art optimization to quite large datasets. We also see that the 199 protocol has increased robustness to measurement imperfections when compared to the 139 protocol, and we present efficient post hoc corrections for datasets that have been acquired with faulty encodings. And such conditions can occur when gradient cross terms cause the b-value to vary among directions, or where maybe encoding directions deviate from the prescribed directions, perhaps due to post-processing, such as co-registration, where B matrices have to be rotated along with the image plane. We think there are many applications for fast kurtosis imaging. Essentially, any setting where time is crucial, or where a estimate of mean kurtosis is needed rapidly, our techniques are applicable. We also think that our technique makes it easier to collect data just for exploration of the utility of DKI in patient groups. We have some early reports on the utility of the technique in brain tumors in this paper from last year. And also we've seen a lot of activity from the Boston group in characterizing these techniques in connection with stroke. The 199 protocol is also efficient enough that datasets can be collected with varying diffusion time, so the time dependence of the kurtosis parameters can be estimated. And we want to point out that these protocols are available as work-in-progress packages for Siemens MR systems, complete with online reconstruction. We also think that fast kurtosis imaging might have use outside of the brain, for instance in imaging of the major organs of the body, where imaging conditions are quite challenging. We have a report coming out in connection with imaging of fibrotic kidneys in MRM Biomedicine, where we apply the 199 technique. Also, I'd like to point your attention to a recent report from NeuroImage, where we show fast imaging of axial and radial kurtosis, and this application study by Eduardo et al., where he uses this technique to evaluate the effect of crack cocaine addiction. This is available on bioRxiv. And then we'd also like to thank our grant sponsors and you for your attention. Thank you.